chapter 9 is officially getting into inferential statistics. So up until now, we've just been doing statistics that were descriptive. So that meant we would find something and just say, okay, this was the population percent or a sample percent, and that's all we would know. We never really applied it too much to the population. So now in chapter 9 and 10, we're actually going to be doing inferential statistics, meaning when I do this with my sample, what does that mean about my population? So chapter 9 is all about estimating. And it's estimating the value of a parameter. Remember, a parameter is the word for when we're measuring a population. So in 9.1, we're going to estimate the population proportion, so that's the parameter. And in 9.2, we're going to estimate the population mean, so that's the parameter, all right? They really are similar. So 9.1's a little bit lengthier because we have to kind of learn the practice of it. And then 9.2 will go a lot quicker. So let's go ahead and see what's happening. It says 9.1, estimating a population proportion. Our goal in this section is to estimate the value of an unknown population proportion. So, in order to do that, we're actually going to start with a point estimate, and that's your first fill in the blank, guys. And what it is, if you read the directions, or excuse me, the definition, it says a point estimate is the value of a statistic that estimates the value of a parameter. A point estimate is exactly what its name is, a point, one single value to estimate, okay? Up until now, we've been using point estimates, all right? So if we don't know the population proportion, we take a sample and we use a sample proportion and so forth. So in 9.1, we're going to be estimating the population proportion. So the best point estimate for a population proportion is the sample proportion. Do you remember what his symbol was? 8.2. If P stands for your population proportion, who is the sample proportion?
N.
Are you guys glad there's not a final? P hat, the party animal, right? If we didn't know the entire population, we just took a sample. Does anybody remember what P hat's formula was? X over N. Yeah, so now that we know who we're talking about, we know how to find him, okay? So that's what we did until now. Like, so 8.2, we didn't know what the population proportion was, so we took a sample and we said, okay, 87% of my class is going to pass the exam or whatever, and that's what we used until now. So starting 9.1 homework, the first couple questions will just be, what's the best point estimate? And you'll just use the p hat value, whether it's given to you or you calculate it using x over n. So let's do this example. It says a study of 74 patients with ulcers was conducted in which they were prescribed medicine. After 8 weeks, 58 reported ulcer healing. Find a point estimate for the proportion of patients with ulcers receiving medicine who reported their ulcers healing. So a point estimate is just one single value, and for the proportion, it's going to be p hat. How do we find p hat? X over n. And you actually had a problem exactly like this on the test. How many total people did we study? Say it louder, I heard it. 74, so that will be our bottom. And of those total 74 patients, how many said their ulcers got better? 58. So you just do that division. Let's round to 3 decimals. What do you guys get to 3 decimal places? 784, does that look right? All right, and I always like to ask the question, what does that mean, right? And you're like, I don't know, I just did what you told me to do. So what it is if we really wanted to use a certain medicine and put it out in the market, we're not just going to put it out in the market without testing it, right? So if they test it with 74 patients and 58 felt better, that sample proportion was a 78% difference. And so that might be one that's worth investigating and looking to put out on the market. Say we tested 74 patients and only 4% felt better. Do you think we're going to go any further with that medicine? No. And so that's all the more, before now, it's all the more we could do. We could just say, I took a sample. This is what I found out about my sample. So I assume if 78% of my sample felt better, 78% of everyone out there that would take this medicine would feel better. But it's not very exact. So that's when we get into objective 2. All right. So objective 2 is going to be constructing and interpreting confidence intervals. So that's going to be what's new. It's going to be an interval now with a lower and upper bound instead of one single point, all right? So we're going to give ourselves a little bit of wiggle room. It says, once you have a point estimate, what do you do with it? How accurate is that estimate? How sure are you that it truly represents the population parameter? For example, the 78%, maybe we just happened to get lucky, and of those 74 people, we got a lot that just really, really respond well to medicine. And then we go and put it out in the market, and only 20% feel better, right? So what we want to do is we want to be a little bit more accurate and say a little bit more about our sample. So then first fill in the blank for objective 2, guys, is a confidence interval. Confidence interval. And again, it's kind of like point estimate where the name says what it is, okay? So a point estimate was a single value that you used to estimate. Now we're going to have an interval, so there'll be like a lower bound and an upper bound, so it's going to be a range. And confidence just means we're going to be a certain amount of confidence. Like I'm 20% sure or I'm 90% sure. We're going to be able to put some kind of confidence on it. So let's see what it says. It says a confidence interval for an unknown parameter consists of an interval of numbers based on a point estimate. And we'll talk a little bit more about that. Let's get a little bit further in with this whole confidence idea. The next fill in the blank is level of confidence. Level of confidence. And it is kind of like a percent. Like, so if you're 90% sure, that means that you're going to expect 90 out of 100 times for it to work, all right? And that's kind of what the definition says. It says it represents the expected proportion of intervals that will contain the actual parameter if a large number of different samples is taken. So we're going to say we do it 100 times, then 90 out of those 100 intervals should have the true population proportion of people whose stomachs feel better after the medicine. So they're going to have us kind of fill this in. This is just using their awkward notation, okay? So confidence level, guys, is basically how sure you are, but they really focus on the opposite, the tails, all right? So if you're 90% sure, alpha is technically the opposite. So what's the opposite of 90%? 10%, okay? And I know it's kind of weird, but we'll talk about that a little bit more in chapter 10. So if you're 90% sure, that means there's 10% in your tail. So there's a 10% chance you could be wrong, basically. Implies that if you took 100 different confidence intervals, each based on the same sample, we would expect how many of those 100 intervals to actually have the parameter if we're 90% sure? How many of the 100 should have the parameter if we're 90% sure? I heard it. Say it. 90, right? If you're 90% sure, that's what percent you'd expect to have it. What's 90% of 100? 90, okay? And then they turn it around and kind of focus on alpha. So 90 of them should have that parameter. So how many wouldn't? 10, okay? And that's going to be the kind of the whole idea of level of confidence, guys. So when we talk about confidence intervals, we're not going to focus on the low ones. Like, how good would you feel if I said, here's a 20% chance you're going to pass this class? That's not telling you a whole lot, right? So you're going to notice a lot of our confidence intervals will be like upper 80s to like 99, all right? But our confidence level, they really focus on alpha, the complement. And again, in chapter 10, we'll talk a little bit more about it. So how did they construct this confidence interval? Here is like a written sentence. I want to draw it though, okay? Because I think drawing it kind of shows it. So off to the side, let's draw our beautiful bell-shaped curve that you guys are better at drawing than I am, okay? So when we go to make this confidence interval, do we ignore the sample or point estimate for sure? No, that's a perfect place to start. So guys, when you go to do your confidence interval, your point estimate will be right in the middle. Your point estimate will be right in the middle. It's a good place to start, right? But the whole idea of an interval, though, is that we want to give ourselves a little bit of wiggle room. So instead of saying, oh, I'm 78% sure that this medicine's going to work, we're going to give ourselves a range. We might say 70 to 86% sure, okay? So that's what this plus or minus margin of error is. So our confidence interval, guys, will look something like this. Right, it's kind of getting hard. Where we'll add our margin of error or we'll subtract our margin of error, okay? This gap is just our wiggle room. It's our margin of error. Can you even see what's going on there, okay? So say my margin of error is 8%. I would start with my point estimate in the middle, and I would add 8% to get my upper bound, and I would subtract 8% to get my lower bound. Kind of like what we did with the empirical rule, right? We put the mean in the middle and we'd add and subtract our standard deviations. That's what we're going to do, okay? So instead of using one single value to estimate now, we're going to say I'm 90% sure that it's between this and this. Does that picture kind of make sense? You guys see what I'm doing there? So the point estimates are our starting point, but we're going to add and subtract our margin of error. So you'll add to get an upper bound. And let's label that upper bound. So I'm going to write it UB for upper bound. And then we're going to subtract our margin of error. So we'll get our lower bound. Who's always perfectly in the middle? Who's always perfectly in the middle? Your point estimate, okay? And on to either side, it's the same amount, okay? So we're going to add and subtract the same amount. So it's this perfectly even, symmetric little confidence interval. All right, these are things to keep in mind. Will I flat out ask you these things on the test? No, but they will make my math lab homework so much easier because they're kind of conceptual things, all right? So let's talk about them and see if I can kind of make them make sense. And you'll have your notes. So like when you're going through your homework, you'll have your notes to kind of refer back to these. So, level of confidence. As your confidence increases, so does your margin of error, okay? So the more confident you are, the bigger your margin of error is because you want to cover your butt. Have you guys heard of CYA? Cover your beep. Yeah, okay. That's basically what it is. If you're going to be 99% sure, you better be 99% sure that it's going to fall in there. So you like have this really big interval. You're like, I'm going to make sure it falls in there. If you're like, yeah, I'm 10% sure, your interval can be really small because you have a 90% chance of it being wrong. All right, look at number 2. See if this makes sense. Sample size. As your sample size increases, your error decreases. Does that make sense? What do we know about increasing sample size? You get more and more accurate, right? So the larger your sample gets, your errors get smaller because you're getting more and more accurate. All right, last one, standard deviation. The more spread your data is, the wider your interval. Does that make sense as well? If your data is really spread, it means it's not very concise, so your confidence interval will kind of mimic that. All right, let's go ahead and flip it over to the top of page 2. And the first thing we're going to do before we can do these confidence intervals is find the one unknown part of the formula. So kind of skipping ahead, I know it looks scary. Skipping ahead down to this formula. You know what p hat is. That's our sample proportion. So you know p hat here, you know p hat here. What's n? Sample size. What's the only little symbol you don't know yet? Z alpha over 2, but actually you know him, okay? And we'll talk about it right up here. So he is new notation, but how we find him is exactly how we did it in chapter 7. Remember when we wanted to focus on the middle 80% of people, and it was that backwards formula? If you had to find the z-scores for the middle 80%, you said, okay, 80% in the middle left how much for the tails? Anybody? 20%, but how much in one tail? 10%. That's what alpha over, I'm throwing pencils. That's what alpha over 2 means. Remember, alpha is your error. It's what's on the outside. Over 2 just means you have 2 tails, okay? So let's look at what's going on here. It says, now how the heck do we construct an interval? Bless you. If we want a confidence level of C, confidence levels will be between 0 and 1, but we don't care about the low ones. So typically, guys, they're going to be 0.90. It's kind of small. I'm sorry if I write small. 0.95 and 0.99, okay? Does that mean these are the only confidence intervals you'll see? No. So when I go through these steps, please make sure the steps make sense because you'll have to do it if it's an 88% confidence interval or a 92% confidence interval. But in any case, the C that we want will be between 2 Z values. Those Z values are exactly how we found them when we found the middle 80% of the data, okay? So if we want to find the middle 90% confidence, that means how much is in the tails? 10, right? But if there's 10 in the tails total, how much are in each tail? 0.05. But remember when I taught this, I said what we want to keep in mind is that this is technically an area. So what we want to do is we want to see what positive z-score correlates to an area of 0.0500. So go ahead and get out your grade sheet. Remember I said that was they're going to follow you till the end of the semester. All right? So we want to see how close, so this is the area, right? This is the area of 0.00 or 0.050. So we're going to look in here. And this is one where it's kind of weird. Notice what happens. I'm going to zoom in a little bit. My chart. Okay. So 0.05 is like around here-ish. And notice what happens right here. Between 0.0505 and 0.0495. Which one's closer? They're the same, right? So they're in between 1.64 and 1.65. So what do? We average them. I'm going to write the average right here, and then I'll write it off to the side where we get it. So write the z-score there, okay? Notice we don't write the negative because the formula will take into account the negative and the positive. So we just want to focus on the positive because down here we'll subtract and down here we'll add. So that negative positive will be taken care of. So your critical values are always positive. And off to the side, if you need to say where this came from, it's because we add negative 1.64 to negative, and I don't even know if you want to put the negative there or not, negative 1.65. If you add them and divide by 2, you get 1.645. It's just halfway in between those two values. Could you pick one or the other? Sure, but you won't be as accurate. So if we're halfway in between, then the z-score will be halfway in between them. 95% confidence is kind of neat, guys. It's one that we actually can find perfectly on the chart. So let's go through the motions to find what area we need to look up. 95% confidence means how much in the tails total? 0.05. But if there's 0.05 left in the tails total, that means how many in each tail? You got it, 0.025. But remember, this corresponds to an area of 0.0250. Okay? I like to write it in 4 decimals so you realize that's the area. So again, we're going to go in our chart and see how close to 0.0250 we can find. And this one you actually find perfectly right here. Okay, and who does he go with? He goes with 1.96. And again, we're ignoring the negative, okay? Our critical values are going to be positive. So this is perfectly 1.96. And that's really rare. All right. 99% confidence means how much is in the tails? 1. And this one just starts getting awkward just because the numbers are small. It's not that we can't do it, but the numbers just get really tiny. So if there's 0.01 left in the tails, how many is left in one tail? 0.005. Which means that corresponds to an area of 0.0050, right? Again, I'm just writing that same exact number, but in 4 decimals. So we're going to go inside our chart and see how close to 0.0500 we can, and it's exactly like 90% confidence, where we're perfectly halfway in between the two. So 0.05, see how it's between these two? So here's 0.0505, and then, no, that's the one that I already did. I got to go smaller, don't I? 00. Eek, even tinier, don't pull Molly. Okay, so here. 0.0051, 0.0049. They're exactly 1 away, okay? So we're going to ignore the negative, and we're going to average 2.57 with 2.58. And what will that give us? 2.575. Okay, and again, we got that from averaging the two values that it's in between. I put the negatives just so you know where to look, but we really aren't using the negatives. Does anybody have any questions on like where we're getting the 0.1s and 0.05s or anything? It's what we did when we did that inverse lookup, right? The middle 80%. That is the only new part of the formula. Otherwise, guys, as much as I hate to use the term plug and chug, that's what we're doing, okay? So here's the puzzle. We'll be given all the pieces, so we'll literally just plug the pieces in, and out will come our confidence interval, okay? Keep in mind, whenever we're dealing with proportions, these two things must be true in order for it to be approximately linear. So typically on my math lab, you hit yes, it's true, because if it wasn't, you guys couldn't keep going on, okay? So if it's only a one-step problem, then maybe it won't work, but if you see steps 1 of 18 or whatever, you know these are true, okay? On the test, I'll focus on that one. I won't worry so much about this one because we rarely know capital N, the population size. You don't usually know that. Okay? So let's see what, this is actually kind of, I try to mimic your homework as much as possible, okay? So the very first thing they're going to give you is they're going to give you the problem, but they'll ask for the point estimate first. So let's go ahead and read what's going on. It says, in October 2003 poll, 684 of 1,006 randomly selected adult aged 18 years or older stated that they think government should make partial birth abortions illegal, except in cases necessary to save the life of the mother. So remember I said stats is always kind of controversial. Let's not worry about that. Let's just talk about the actual statistics. So obtain a point estimate for the proportion. So remember, a point estimate is just one single value. If you had to give me one single value to estimate the true population proportion, what would be the next best thing? The sample proportion p hat, okay? So anytime they ask for a point estimate for the proportion, it will always be p hat x over n. What's my x? What's my n? You got it. Remember, you can't have it flip-flop, because if you have it flip-flop, it's greater than 1, right? So we asked 1,006 people, so that was the bottom, and 684 said yes, they agree with that. And so you just throw that into your calculator, and what do you guys get? 0.67. So it goes for a while. Let's do 3 decimals. I think it's still like 0.680, but I want to be consistent, okay? So even though you want to put 68, it's not really 68, we'll put 0.680 to be, I think they typically do 3 decimals, okay? So on your homework, the first part of every word problem will be the point estimate, okay? And that's what you've done up until now. Then the second part will say, we'll make sure that it is approximately normal, and then we're going to go on to our confidence intervals. So the first one is, let's look at this inequality first. N times P times 1 minus P, is that greater or equal to 10? Question mark. And I'm just going to do it right below it. Is your sample size times, oh, and I think it's P hat because we don't know P, we're trying to estimate P, times your sample proportion times 1 minus your sample proportion greater or equal to 10. So that is different. Before we used P, but since we don't know P, we're trying to estimate P, what's the next best thing? P hat, okay? So what was our N? How many total people did we ask? 1,006. What was our p hat we just found? 0.680. And then we're going to do 1 minus 0.680. And the question is that greater or equal to 10? So what's nice, guys, is you can put it in your calculator exactly like that. Take your 1,006 times your 0.680 times parentheses 1 minus 0.680, and you should get a number that's greater than 10. I think this one's easily greater than 10. Is it like 219-ish? Yeah, okay. So it's 219, which is greater or equal to 10. Check. So that's met. Does everybody see what we're doing? So we're trying to fulfill that this inequality on the left is greater than 10, and it is. The second inequality, we'll talk about it in our notes, but I don't worry about it as much on the test. Is our sample size easily less than 5%? Yes. 1,006 is easily less than 5% of all adults in the U.S., okay? So we'll just say yes, 1,006 is less than 5% of all adults. And that one we just talk about because we were not given capital N, how many total adults there were in 2003 in the U.S., okay? But we know 1,006 is easily less than 5% of it. All right, so when you flip it over, what I want to do, since it's still the same problem and I don't want you to flip back and forth, what I want us to do is right up here, our N was 1,006. Oh, I'm writing really high, sorry. Our N was 1,006. P hat was 0.680, okay? Kind of keep that in mind. That's just what was given to us. All right, so we're going to construct a 98% confidence interval for the true population proportion for this problem. So you keep your notes here. I'm going to flip back to the formula. I kind of skipped the formula. I got excited here, okay? So the lower bound and upper bound, notice them. They are exactly the same. What's the only difference? The lower bound, what do we do? Subtract. The upper bound, we just add, okay? So what we're going to do is we're going to find the lower bound, and we're going to leave p hat alone, and we're going to find this chunk. That's your margin of error. We're going to subtract it to get our lower bound. We're going to add it to get our upper bound, and then I'll say, guess what we can do in our calculator? This. So this might be the only time that you actually use the confidence interval formula, okay? Because our calculator doesn't, all right? So for our lower bound, I just label it LB, okay? You have p hat minus z alpha over 2 times the square root of p hat times 1 minus p hat all over n, okay? So it's like, you guys can't read it when it's sideways like that. So we have p hat, so we're going to start with our point estimate of 0.680, and we're going to figure out this chunk. This chunk's called the margin of error. How we find the margin of error is we take our critical value, z alpha over 2, times basically the standard deviation, right? P hat times 1 minus p hat all over n. Once we calculate this chunk, we're just going to add it to get our upper bound. Okay, so p hat minus z alpha over 2, and this is just times, this is just right next to each other, the square root of p hat 1 minus p hat over n. And like I said, this is our puzzle. We're going to plug things in now because we have all of our pieces. What did we calculate our p hat to be? And you'll have already done that on your homework as well, okay? So part A, you had already figured out what p hat was, okay? So grab that from part A and plug it into this formula. So we have 0.680 minus, let's leave a gap because he's like the one thing we actually have to calculate, okay? So let's leave this gap and let's fill in the square root, 0.680 times 1 minus 0.680 all over n. What was our n? 1006. Okay? So the one thing we actually have to calculate is we have to calculate what that critical value is, and that critical value is always based off of him, your confidence, okay? So let's see. We'll do it off to the side. We'll do like a little arrow. Here we go. This is where he's going to come from. So 1 minus 98 leaves how much for our tails total? 0.02. 1 minus 98 leaves 0.02 for our tails total, right? But how many tails do we have? 2. So what do I need to do? Divide by 2 tails. So I'm really going to look up an area of what? 0.0100. So I'm trying to do, sorry, it's like a footnote. Like, where is this number going to be coming from? That number is going to be coming from our confidence. So since we were 98% confident, that means we had a 2% of error in our tails, but we have 2 tails total, all right? So we're going to divide by 2 to just find how much hair area is in one tail. Now go look on your chart just like we did in chapter 7 to see how close in here you can find a 0.01. It's not price of right rules, it's literally how close can you get. So 0.01, here's 0.0102, but then here's 0.0099. So who's closer? The 99. What z-score does he go with? 2.33. Ignore the negative, right? So in this formula, we'll do 2.33. Are there any questions at all where that z came from, guys? That's the one part that you'll have to know how to calculate, okay? Because even though your calculator will be doing this formula for you, I am going to have some problems on your test that just say, what's the critical value? So you do need to know how to find that. Are there any questions on that? Okay, so this is what we're going to do. We're going to let 0.680 hang out as we calculate this, because then we'll just add that to 0.68 to get our upper bound. So in your calculator, you can put it in exactly like that. So you can do 2.33 times the square root of 0.680 times 1 minus 0.680 over 1006. Round to 3 decimals, so like whatever you round your p hat to, round that margin of error to that. When I did that, I got 0.034. Are you guys getting that when you put that in? Okay. Keep in mind, it's kind of like a give or take, all right? So if we're talking about what